Have you ever heard of the quantum world? Not the kind we encounter in Christopher Nolan films or Marvel stories, where quantum realms are portals for spectacle and superheroes, but the real quantum world, the one that quietly governs the fabric of reality itself. This is the world that operates beneath everything we see, touch, and assume to be solid. A world where certainty dissolves into probability, where objects do not always have definite positions, and where events are not fully determined until they are observed. It is a world so counterintuitive that even the physicists who built its mathematics still argue about what it truly means. In this journey, we will follow how that strange logic rises from the tiniest scales of nature to shape the technologies that define modern life, from atomic clocks and GPS to lasers powerful enough to measure the universe, and detectors sensitive enough to hear black holes collide. Step by step, we will see how ideas that once sounded abstract now quietly govern how we navigate the world. And at the heart of it all lies an unsettling suggestion that reality itself may not be fully formed when no one is looking. That the act of measurement, the act of interaction, plays a role in deciding what actually happens. Stay with this question, because by the end, this is not just a story about quantum physics. It is an invitation to rethink what reality means, what observation really is, and why the universe may be far less solid and far more fascinating than it appears. So, before we go any further, it is only fair to admit something. The deeper we look into the quantum world, the less it is going to behave like the world your senses have spent a lifetime training you to trust. There is a reason people joke that quantum physics is a reliable way to get a headache. Your mind is built for falling apples and whirling planets, for doors that are either open or closed, for lights that are either on or off. It is not built for particles that seem to be spread out and localized at the same time, for events that are neither fully real nor fully unreal until something, somewhere, forces the issue. In that sense, confusion is not a failure here. It is a sign that your intuition has finally wandered into territory it was never designed for. And yet, in that very territory, our civilization has quietly built its most reliable tools. Quantum mechanics is not an obscure speculation hiding in a dusty corner of theory. It is the most precisely tested framework in all of physics. When engineers design the chips that sit inside your phone, when they shape the components that steer light inside fiber optic cables, they are following rules written by a quantum description of matter and energy. You can refuse to follow the equations, but you cannot refuse to live inside the world they predict. If you could freeze your everyday life and strip away the surfaces, underneath you would not find a smooth, classical machine. You would find layers of quantum behavior, piled on top of one another, stabilized by scale and statistics into something that feels solid. The screen you are watching now glows because electrons in carefully engineered materials jump between allowed energy levels, releasing light at specific frequencies when they fall. The flash of a simple light-emitting diode is already a quantum event. Consider the device that keeps global time. Atomic clocks do not rely on the swing of a pendulum or the turning of a planet. They rely on the fact that atoms have sharply defined energy gaps between their internal states. When an electron in a cesium atom shifts between those states, it absorbs or emits radiation at an exquisitely stable frequency. We agree to call a certain number of these oscillations 1 second. The rhythm of the modern world, from navigation systems to financial networks, rests on microscopic transitions in clouds of atoms, vibrating in vacuum chambers no one ever sees. Notice the asymmetry. At the human scale, you experience a world of tables, streets, and sky. At the quantum scale, the world is described by abstract symbols on a page, by wave functions and operators and amplitudes, by machinery of probability that almost no one encounters directly. And yet, it is that hidden description that reliably shapes the devices you use. The medical scanners that peer inside bodies. The lasers that read information from plastic discs or send it along glass fibers beneath oceans. The very ordinary has been quietly built on something deeply non-ordinary. This creates a strange kind of double life. In daily routines, you move through a world that seems continuous and self-contained. You act as if everything around you would continue existing in the same way, whether or not anyone were there to witness it. You pour coffee, lock doors, check messages, assuming that the objects involved have definite positions, definite properties, definite stories that carry on without you. It feels almost immoral to question that. To doubt the solidity of the mug in your hand feels like doubting the solidity of your own place in the world. Quantum mechanics does not attack that feeling directly. It does something subtler. It tells us that the underlying description of matter does not use the same language you use when you think about mugs and doors. It offers a rulebook that speaks in probabilities and superpositions instead of indefinite trajectories. It tells us that when no one is measuring an electron inside a transistor, we should not imagine it following a single sharp path. We should imagine a spread of possibilities, a wave of potential behaviors that only produces a concrete outcome when the right kind of interaction occurs. You might be tempted to split your world in two, a familiar realm where things are definite, and a strange underworld where they are not. Many people do that, even many scientists. But the boundary is not as clean as it first appears. The rules that govern electrons in a chip also govern atoms in your retinas, molecules in your brain, and the detectors in vast experimental halls. There is no separate classical universe waiting above the quantum one. There is only one universe, behaving according to quantum rules, which just happen to simplify into something more familiar when enough particles are involved. That is why some physicists say that we are already living in a quantum age. Not because we have suddenly crossed a threshold and entered a new era, but because we have finally learned to exploit rules that were always there. The global economy depends on semiconductor physics, on lasers, on sensors that can detect single photons of light. The internet depends on the stability of quantum states in materials designed atom by atom. Every time you unlock a device with your fingerprint, an invisible chain of quantum-based technologies is set into motion. All of it taken for granted, almost all of it unseen. There is a quiet unease hiding in that realization. If the most accurate theory we have insists that nature at its core is described by probabilities, what exactly are we living in? A world of solid facts? Or a world of outcomes distilled from countless unrealized possibilities? When you press a button, you are not negotiating with certainty. You are making a kind of peace with overwhelming likelihood, so long as the device behaves as expected. The question of how many microscopic chances had to cooperate for that to happen fades into the background. But the question does not disappear. It waits at the edge of attention, especially at hours of the night when the world is quiet. And the glow from a screen becomes the main evidence that anything exists beyond your thoughts. How much of what you call reality is simply the stable average of countless quantum events playing out beneath awareness? How much of your confidence in the solidity of objects is an act of faith in the statistics of large numbers? The unsettling part is that quantum mechanics does not offer an easy story to soothe that discomfort. The equations tell you how to compute the probability that a measurement will give one result or another. They do not tell you what the system is doing in between. They do not tell you whether the world is secretly deterministic under the surface, or whether indeterminacy is truly woven into existence. Physicists have written whole libraries of interpretations trying to answer those questions. And the experiments keep telling us the same thing. The probabilities are right. The outcomes match. The devices work. Beyond that, nature stays silent. In a sense, we have built an entire civilization on top of a black box. We know how to feed inputs into the quantum machinery of the world and how to read off the outputs with astonishing precision. We do not fully know what, if anything, exists inside that box, in the way our intuition wants. We pretend that the surface story is complete, because it is enough to go to work, to send messages, to get from one city to another. But somewhere underneath those routines is a description of reality that does not quite fit any of our inherited pictures. Living in the quantum age means accepting this split. It means using a microwave oven without needing a mental image of every electron involved. Trusting a medical scan without imagining every photon bouncing inside a detector. It also means acknowledging that the success of these technologies is not proof that our ordinary concepts of objects and causes are exact. Their success may instead be telling us that reality, at the deepest level we know how to test, is stranger than the stories we grew up with and more resistant to being captured in a single, comforting picture. There is a peculiar humility in that. For most of human history, power and understanding seemed to go together. To control something was to claim that you understood it. The quantum world breaks that link. We have learned to control processes we may never fully visualize. We can summon effects that do not sit comfortably inside any metaphor. We can navigate a world whose operating system we can write down in symbols, while still not knowing what kind of thing that system is. And this is only the beginning. The same rules that make your devices function are also the ones we now use to build new generations of sensors, clocks, and computers. The more precisely we learn to manipulate quantum systems, the more we are forced to confront what, exactly, those systems are doing when we are not looking. As our instruments become more sensitive, the gap between how we talk about reality and how it appears to behave will only grow more obvious. For now, it is enough to keep one quiet thought in mind. The age you live in is not just defined by the scale of your cities or the reach of your networks. It is also defined by the level of reality you can affect without really understanding. In that sense, the quantum age is not ahead of you. You are already inside it, carrying it in your pocket, resting your head next to it as you fall asleep, surrounded by technologies that depend on processes no one ever directly sees, unfolding in a world that may not be as fully formed, or as independent of its observers, as it once seemed. If quantum rules can hide inside the electronics on your desk, they can also hide in something much larger, in a faint mark on a graph that quietly suggests the sky is not what it seems. Decades ago, before anyone spoke with confidence about black holes, astronomers were already trying to hear the universe in kinds of light no human eye can see. High-energy X-rays are stopped by the atmosphere, so detectors were bolted to sounding rockets and fired briefly above the air, given only minutes to listen before falling back. Their memories stored as ink, paper, and magnetic tape. During one such flight in the year 1964, one instrument recorded an unusually intense source of X-rays in the direction of the constellation of the Swan. Later, it would receive the label we now use. But in that moment, it was only a stubborn spike in the data, a small rise that refused to blend into the background. No one watched a star disappear. No one saw a dark circle in the sky. All that existed, at the beginning, was a disagreement between what the theory predicted and what the detector quietly insisted was there. The safe move was to blame the tools. Perhaps the detector was miscalibrated. Perhaps the rocket tumbled. When we carry a quiet belief that the universe is already settled, already behaving according to familiar rules, it feels more reasonable to doubt our instruments than to doubt reality itself. The background assumption is that the world out there is complete. If anything does not match, the error must be on our side. But the strange source in the Swan did not vanish with better hardware. When more sensitive satellites were launched, able to stare for long stretches instead of merely glance, they saw the same patch of sky flicker and flare in X-rays. The brightness jumped on very short timescales, so quickly that whatever produced those rays had to be compact. If different parts of a source are separated by large distances, light needs time to travel between them and smooth the changes. Rapid flicker points to a smaller stage. and a smaller stage demands more extreme gravity to power it. Over time, astronomers matched the X-ray source with what looked invisible light, like an ordinary hot blue supergiant star. That star was moving, rocking back and forth as if pulled by a massive companion that refused to show itself. The visible star could not, by itself, account for the furious X-ray emission. Something nearby was drawing gas off its surface, swirling that gas into a disk, and heating it so intensely that it glowed in high-energy light before plunging out of sight. At first, there were gentler explanations. Perhaps the hidden object was a neutron star, already exotic, but still within the boundaries of what felt acceptable. As measurements improved, though, the estimates of the unseen mass climbed. The compact companion appeared to be roughly 21 times the mass of our Sun, too heavy to be supported by the physics that holds up a neutron star. The most cautious remaining interpretation was also the most severe. The data matched what general relativity predicted for a black hole. Notice how little of this begins with grand declarations about the nature of reality. The chain starts with a few minutes of data from a rocket flight, continues with years of repeated satellite observations, and only slowly corners us into admitting that an invisible, extremely dense object is there. Our picture of the cosmos bends under the weight of accumulated measurements, not under the weight of our preferences. When we say that this system sits about 7,000 light-years from Earth, we are not describing a distance that anyone will ever cross. We are describing a carefully stitched web of inferences. Tiny shifts in the star's apparent position as the Earth orbits the Sun, models of how bright such a star should be. The known speed of light that ties time to distance. Many fragile strands are drawn together until a single estimate feels stable enough to use. The distance is less a naked fact we have found, and more a point where different ways of looking stop contradicting one another. In that sense, the black hole is not something we see. It is a conclusion that refuses to go away. No telescope resolves its outline. What we have instead are consequences. The sway of the visible star, the heat of the accretion disk, the pattern of flickers in X-rays and murmurs in radio waves. The unseen thing becomes real for us because every independent line of evidence curves toward the same invisible center. For the system in the Swan, that map of consequences includes an orbital rhythm. The visible star and its unseen companion circle their common center of mass roughly every 5 and a little more than a half days. Astronomers read this period from tiny shifts in the star's spectrum and subtle changes in its brightness as its shape is stretched by the gravity of its partner. To talk about that orbit from here, on a small world far away, is already to stand at the end of a long chain of transformations. From distant gas, to radiation, to electrical pulses, to numbers, to a quiet mental image of one star tugging another around an invisible point. Seen this way, the simple question, what is really there, becomes harder to answer cleanly. Somewhere in that distant system, there is surely some configuration of matter and space-time, evolving according to whatever rules truly govern the universe. Yet for us, what exists is entangled with the measurements and inferences that bring it into awareness. The black hole is both an object that would continue without us and a pattern in the information we have managed to extract. It is a compromise between what the cosmos does and how a finite mind, using finite instruments, is able to describe it. Black holes push this compromise to an extreme because they set a hard limit. Once matter or light crosses the event horizon, no signal from inside can ever reach us. According to our current theories, from our vantage point, the story ends at that boundary. The interior might contain intricate structures, violent events, even whole histories of infalling matter, or it might be describable, at some ultimate level, by a geometry so extreme that our familiar ideas of space and time lose their meaning. Either way, none of it will ever appear in any human record. For beings like us, the inside of a black hole is not just unknown, it is unreachable. The path from a small excess in X-ray counts on a mid-20th century rocket flight to the quiet conviction that a black hole orbits a supergiant star in the Swan. On its surface, a technical success. Beneath that surface, it is also a lesson in how thin our grip on the cosmos really is. We infer an extreme object from the way it perturbs its surroundings, the way a hidden weight can be guessed from the way a table bends beneath it. We never touch the weight itself. We live among the consequences, somewhere, far beyond the reach of any spacecraft now imagined. Gas is still falling toward that unseen horizon. Photons still skim past and escape, carrying away the last traces of what happens just outside. Our instruments gather a few of those photons. Our theories turn them into a narrative about collapsed stars and warped spacetime. Between what unfolds near that invisible boundary and the story forming in your mind as you listen, there is a gap that will not close. We live inside that gap. The same distance separates your everyday sense of a stable world from the quantum rules that govern its smallest parts. Black holes merely make that distance harder to ignore. They begin as minor disagreements in the data and end as quiet reminders that there are places where reality carries on without us, in ways we may never fully describe, no matter how long we keep listening. And sometimes, when we listen long enough, the silence around those unreachable places starts to sound less like nothing at all, and more like a background hum we had never learned to hear. The idea that so-called empty space could have a role in shaping the fate of a black hole did not begin with a telescope pointed at the sky. It began with equations, with a puzzle at the edge of two powerful theories that were never designed to coexist. General relativity draws a smooth, continuous picture of space-time, bending gently or violently under the influence of mass and energy. Quantum field theory describes a world where fields never quite settle, where fluctuations are built into the structure of reality, even in what we would normally call a vacuum. For a long time, those two pictures were kept in separate rooms. Black holes belonged to gravity. Quantum fluctuations belonged to particle physics. Both were successful within their domains, and it was tempting to treat them as neighbors who never needed to speak. The event horizon of a black hole looked, in classical terms, like a clean boundary. Cross it, and no light ever comes back. The vacuum around it looked, in that same classical language, like nothing at all. Then, in the early 1970s, Stephen Hawking followed what happens when quantum fields are allowed to live in the curved spacetime near a black hole. In the year 1974, he published a calculation that did not seem to leave room for denial. A black hole should not be perfectly black. It should emit radiation, with a spectrum like that of an ordinary hot object, as if it had a temperature. The popular image of this process is almost cinematic. You may have heard the story. The vacuum seethes with particle-antiparticle pairs that briefly appear and annihilate near the event horizon. One member of the pair falls in while the other escapes. The escaped one becomes a real particle, its partner, swallowed by the black hole, carries negative energy and slowly saps the hole's mass. That picture is only a metaphor, but it is not a careless one. In the more precise language of quantum field theory, the vacuum is described by a state that depends on the geometry of spacetime and on how observers define positive and negative energy. Near the horizon, what looks like empty space to a freely falling observer does not look empty to someone who hovers just outside, firing rockets to avoid being pulled in. The boundary between those perspectives is where the possibility of radiation appears. Hawking's calculation, in its dry mathematical form, treats the black hole as a background and asks how a quantum field behaves there. The surprising answer is that, far away, the field looks as if it has been in contact with a hot surface. Particles emerge with a characteristic distribution of energies, as though the horizon itself were glowing. The temperature of this glow, now called the Hawking temperature, is inversely proportional to the mass of the black hole. Larger holes are colder, smaller holes are hotter. For a black hole with roughly the mass of our Sun, the Hawking temperature is calculated to be about 60 nanokelvin, a warmth so low that it lies tens of millions of times beneath the temperature of the cosmic microwave background that fills space. In practice, that means such a black hole does not sit there quietly evaporating. The universe around it, with its faint bath of microwave photons left over from the Big Bang, is warmer than the hole itself. The black hole absorbs more radiation than it emits and slowly gains mass instead of losing it. Only when you imagine much smaller black holes does the balance shift. As the mass shrinks, the Hawking temperature rises. The hole emits more energetic particles. The radiation carries away more energy. The mass decreases faster. In Hawking's original treatment, the endgame is a runaway process. The smaller the black hole becomes, the hotter it gets, until its final moments are a burst of intense radiation. For tiny hypothetical black holes, perhaps formed in the early universe, that final flash might come within a manageable span of cosmic time, short enough that we could hope to see the echo in high-energy gamma rays. So far, no such conclusive signal has been found. For stellar mass black holes, the story unfolds on a different timescale. The time it would take a black hole with the mass of the Sun to evaporate purely through Hawking radiation is estimated to be on the order of 2 × 10 raised to the power of 67 years. That is not a number you can picture. It is not even a number your lifetime, or the lifetime of your species, can meaningfully relate to. It makes the current age of the universe feel small. The evaporation of ordinary black holes, if nothing else intervenes, belongs to a future so distant that almost everything familiar will have already dissolved. This is where the phrase "empty space is not empty" becomes more than a slogan. The vacuum, in quantum field theory, is not the absence of everything. It is the lowest energy state of a set of fields, a state still alive with fluctuations, correlations, and possibilities. Those fluctuations can be described by modes of the fields that extend over vast distances. When space-time is curved, different observers cut those modes up in different ways. What looks like calm emptiness from one vantage point can look like a thermal bath from another, near the horizon of a black hole. That difference in perspective has real consequences. Particles that appear to be streaming away to a distant observer can be traced in the mathematics. Back to vacuum fluctuations near the horizon. The same horizon that classically marks a point of no return becomes, in quantum terms, a semi-permeable surface through which information about the black hole's mass and spin can leak out as heat. There is a quiet irony here. The very concept designed to wall off a region of space-time from the rest of the universe ends up being the source of a communication channel. The radiation emerging from just outside the horizon carries no details about what fell in. It is thermal, almost featureless, but it still encodes, in its very existence, the statement that the black hole has a finite temperature, a finite entropy, and therefore a finite capacity to store information. That conclusion deepens, rather than resolves, the old sense of unease. If a black hole radiates away its mass and eventually disappears, what happens to the information about everything that ever crossed its horizon? Does it leak out? Scrambled beyond recognition? Does it linger somehow in a quantum imprint on the surrounding fields? Or is there, at the most fundamental level, a failure of the rule that says information is never destroyed? These questions have grown into what is now called the black hole information paradox. It has pushed physicists to examine the seams of quantum theory and general relativity more closely than ever. Proposals have multiplied. Subtle correlations in the Hawking radiation, exotic structures at the horizon, holographic descriptions where the interior is encoded on a lower dimensional boundary. None of these options sit entirely comfortably with intuition. Each one reshapes what we mean when we say that something really exists inside a region we can never access. On the surface, this sounds remote from everyday life. No one you know will watch a black hole evaporate. No one will drift across an event horizon, carry information into the interior, and then wait to see whether it reappears in the outgoing radiation. Yet the questions raised here are not confined to distant astrophysical monsters. They touch something more immediate. How much of reality is defined by what can, in principle, be known? In classical physics, it was easy to separate the two. There was what exists, and there was what you happen to know about it. A stone rolling down a hill follows a path, whether or not anyone touches it or sees it. In quantum theory, especially once black holes and horizons enter the scene, that separation becomes less clear. The structure of the vacuum, the way fields fluctuate, the way they appear as particles to different observers, all of that is tied to which questions can be asked and which measurements can be made. Hawking radiation is a reminder that even the most extreme objects in the universe are not exempt from this. A black hole is not a static, eternal hole carved out of space-time. It is a thermodynamic object, with a temperature and an entropy, exchanging energy with the quantum vacuum around it. Over incomprehensible stretches of time, it loses mass, slowly fading into the same restless sea of fluctuations that helped define it in the first place. It is unsettling to realize that the ultimate fate of something as heavy and decisive as a black hole may be to vanish into a bath of faint radiation, leaving only ripples in the surrounding fields. But at the same time, there is a certain consistency in the thought. If empty space is never truly empty, if it is always alive with potential, then even the most solid objects are temporary arrangements within that deeper, fluctuating background. They appear, evolve, and, given enough time, they dissolve back into it. From our position, in a small corner of a galaxy, during a short human century, we mostly ignore this. We have to. Life is lived at scales where horizons are metaphorical and vacuum fluctuations have no visible consequences. Yet at quiet hours, it is possible to feel the tension between the permanence we crave and the instability written into our best theories. The same quantum fields that allow atoms to exist, that give matter its structure, also whisper that nothing configured out of them lasts forever. For now, much of Hawking radiation remains a theoretical prediction, tested indirectly through consistency with quantum principles and gravitational theory rather than through direct observation. The expected signal from astrophysical black holes is too faint, drowned beneath the warmer glow of the universe itself. Physicists have tried to mimic the effect in laboratory systems that have horizons of a different kind, in fluids and optical materials where waves face a point of no return. Some experiments hint at similar thermal emissions, but the connection to real black holes is still carefully debated. So we live with an odd arrangement. Our best understanding of how quantum fields behave in curved spacetime tells us that black holes have temperatures, radiate, and evaporate. Our telescopes cannot yet see that process unfolding. Between those two facts, we build a picture of a universe in which even emptiness is active, in which horizons are not just boundaries of ignorance, but participants in the story. Somewhere, unimaginably far in the future. If the theory is right, and if no new physics intervenes, the last black holes will complete their long evaporation. Their final photons will spread into a cosmos already thinned of structure. A universe in which almost all traces of the present have blurred into uniformity. No familiar observer will be there to watch that happen. Yet the possibility that this is the direction in which things are heading flows directly from how we currently describe empty space. To sit with that thought is to feel, for a moment, how small our usual sense of solidity really is. The walls around you, the devices you use, the stars you see when you step outside at night. All of them are temporary patterns in restless fields. Even the deepest wells of gravity we know how to imagine are not exempt. They, too, leak, fade, and eventually disappear into the background they once seemed to dominate. The strangest part is that almost everything we know about this dissolving universe reaches us in the same way. Carried on waves of light that, for a long time, we thought we understood. By the closing decades of the 19th century, light seemed, at last, to be a solved problem. Maxwell's equations had woven electricity and magnetism into a single, elegant theory in which light was just a self-propagating wave of electromagnetic fields. That picture fit beautifully with everyday experience: ripples in water, sound in air, light in space. A wave was something you could imagine. It spread. It interfered. It diffracted. It felt continuous, smooth, almost reassuring. Physicists began turning that confidence into precise tests. One of the most important involved objects called black bodies, idealized cavities that absorb all radiation that falls on them and re-emit it with a spectrum determined only by their temperature. Experiments measured how much energy these bodies radiated at each color of light. Classical theory predicted that the intensity should climb without limit at short wavelengths. A result so absurd, it earned a nickname: the ultraviolet catastrophe. Yet, the laboratory curves did not explode into infinity. They rose, peaked, and fell. The crisis was quiet, almost bureaucratic at first. You have a set of equations that have worked everywhere else. You have data that refuse to obey them here. Something has to give. In the year we now call 1900, Max Planck approached the problem from a different angle. He imagined that the oscillators of charge in the cavity walls could not exchange energy with the radiation field continuously. Instead, they had to do it in fixed lumps. The energy of each lump was proportional to the frequency of the light. It was a desperate move, made to fit the curve, not to rewrite the world. Planck himself treated the assumption as a mathematical trick, something provisional, not a new ontology. But once the idea was in place, it was hard to keep it confined. If energy comes in quanta for the oscillators in a cavity, perhaps that discreteness belongs to light more generally. Perhaps what we call a beam is not a continuous flow of stuff, but a large collection of individual packets. A few years later, experiments on the photoelectric effect pushed that suggestion further. When light shines on a metal surface, electrons can be ejected. Classical wave theory said the energy of those electrons should depend on the intensity of the light. The way the violence of ocean waves depends on how much energy you pump into them. Instead, researchers found something stranger. Below a certain frequency, no electrons emerged. No matter how intense the light, above that frequency, electrons appeared. And their energies rose with frequency, not with brightness. In 1905, Albert Einstein took Planck's reluctant quantization seriously. He proposed that light itself behaves as if it is made of discrete quanta, later called photons, each carrying an energy proportional to its frequency. A single photon strikes a single electron and either has enough energy to free it or does not. The threshold frequency is no longer a mystery. It is the line between photons that can knock electrons out and those that cannot. This explanation, extending the quantum idea from oscillators to light in general, would later be singled out when Einstein was awarded the Nobel Prize in Physics. With that step, light fractured. On one side stood the successful wave description, explaining interference and diffraction, showing up in the patterns from slits and gratings. On the other stood a particle-like description, explaining how light transfers energy in discrete chunks in processes like the photoelectric effect. The more closely people looked, the less it was possible to say that light was simply one thing or the other. It behaved as a wave when you asked certain questions, and as if it were made of particles when you asked others. This was not just a technical inconvenience. Light is the main way the universe reaches us. It carries information from the surfaces of stars, from glowing gas, from distant galaxies whose shapes are smeared by the expansion of space. To discover that your primary messenger refuses to fit into a single, coherent picture is to discover a crack in your relationship with reality itself. What you thought was a straightforward correspondence between what is out there and what arrives as light becomes more complicated. At the same time, matter began showing the opposite kind of ambiguity. If light, which had been considered a wave, sometimes behaved like a particle, then perhaps matter, which had been considered particulate, might sometimes behave like a wave. Louis de Broglie proposed that every particle with momentum should be associated with a wavelength. It was a bold symmetry. The world would no longer be divided cleanly into wave stuff and particle stuff. Everything would live in a hybrid category. The proposal might have remained speculative, but within a few years experiments put it to the test. In the 1920s, Clinton Davison and Lester Germer scattered electrons from a nickel crystal and found diffraction patterns, the same kind of repeating fringes that had marked light as a wave in earlier experiments. Electrons, undisputed particles of matter in other contexts, were now producing wave-like interference. By then, the crisis of light had expanded into something larger. The old categories were no longer reliable. Objects and fields refused to stay put in the boxes designed for them. Light could not be reduced to a wave or a particle. Electrons could not either. Underneath, something else was at work, described by a new mathematical machinery that did not resemble the gears and orbits of classical mechanics. Out of that tension, quantum mechanics emerged. It did not arrive all at once, as a single finished theory, but in overlapping steps. Erwin Schrödinger wrote down a wave equation whose solutions described the allowed states of systems like the hydrogen atom. Werner Heisenberg developed matrix mechanics, focusing on observable quantities and their transitions. Paul Dirac synthesized different approaches into a more unified framework. The details belonged to the mathematicians and theorists, but the driving pressure came from light and matter refusing to behave in a classical way. At a certain point, the debate could no longer be contained in private letters and small meetings. In the late 1920s, a group of the era's leading physicists gathered in Brussels at what became the famous Fifth Solvay Conference to argue about what the new theory meant. In the now iconic photograph from that meeting, almost 30 people sit in rows, well over half of them either already held or would later receive Nobel Prizes. In the center of the front row, Einstein and Niels Bohr sit a few seats apart, representatives of two different instincts about what kind of reality the equations describe. Einstein worried that the new theory replaced a solid picture of the world with something incomplete. He was dissatisfied with probability at the fundamental level, with the idea that the theory might not be telling us the full story of what exists. Bohr believed that the trouble lay not in the world but in our expectations. Quantum mechanics, he argued, did not need to describe an underlying set of classical trajectories or hidden variables. It needed only to give correct predictions for the outcomes of experiments. And it did that with astonishing success. Behind their technical arguments was a quieter question. How much are we entitled to say about a world we can only access through experiments that themselves disturb the systems we probe? Light, once assumed to be a transparent carrier of information about things as they are, had revealed itself as a participant in those experiments. Not just a witness. Shine light of one frequency and intensity, and you get one set of behaviors. Choose another, and the system responds differently. There is no view from nowhere, no observation that leaves the observed untouched. That realization seeps outward. It is tempting, in everyday thought, to imagine the universe as a kind of stage on which events unfold. with observation being an optional extra. Quantum mechanics suggests a more entangled situation. The conditions under which you ask a question, how you prepare a system, how you measure it, help define the kind of answer that can exist for you. Light does not simply reveal the pre-existing state of an electron. It participates in bringing about the event you record. There is a kind of loneliness in recognizing this. We are creatures who depend on light for almost all of our knowledge of the cosmos, from the small to the grand. Yet the more precisely we understand light, the more we realize how indirect that knowledge is. We never meet the world unmediated. We meet it filtered through quanta that carry only certain kinds of information, produced under conditions we have set. From a technical point of view, the birth of quantum mechanics is a story of equations replacing other equations, of spectra being fitted, of anomalies being resolved. From a more human point of view, it is a story about learning that the intuitive picture we carry of a fully definite, continuously existing world may not survive careful scrutiny at the smallest scales. Light, the thing that lets us see, became the thing that forced us to admit how limited our seeing really is. And yet, we go on. The same quantum rules that unsettled the old certainties now underpin technologies woven through everyday life. Lasers, transistors, LEDs, solar cells, all draw on the idea that light and matter exchange energy in quanta. We have learned to work with a description of reality that does not always yield to visualization, and to extract stable, reliable outcomes from a framework that leaves some deeper questions unanswered. The crisis of light did not end with a clean resolution. It ended with a new kind of compromise, a theory that tells us how to calculate probabilities for measurement outcomes, without insisting on a single story about what light really is when no one asks. It is a compromise that will follow us into every quantum phenomenon from now on. A background awareness that even our most successful descriptions of the world may be less about what exists in itself and more about the thin slice of it that can appear when we interact with it. It is almost a relief. After that, to return to a picture of the world where things simply are, whether or not anyone is there to ask them questions. Long before quantum mechanics, physics had built such a picture. It was not born out of nostalgia, but out of success. From the motion of planets to the swing of pendulums, the same basic rules seem to apply. Give a system a set of initial conditions and a set of forces, and the future would follow. No surprises, no ambiguity. The universe could be treated as a kind of vast, precise machine. In this classical view, a particle is always somewhere. A planet traces a definite path. A stone thrown into the air has at each instant a specific position and a specific velocity, even if you do not happen to know them. The laws of motion do not flirt with probability. They take what exists now and carry it forward, step by step, as if the entire history of the world were inscribed in its present state. This way of thinking reached one of its clearest expressions in an image proposed by Pierre-Simon Laplace. Imagine, he wrote, an intelligence vast enough to know, at one moment, the positions and velocities of all particles in the universe, and to know the forces acting between them. For such a mind, past and future alike would be laid out. Nothing would be uncertain. Nothing would be merely probable. What feels like chance to us would appear, from that vantage point, as ignorance of a script already written. The dream here is not just one of prediction. It is a dream of reassurance. If the universe is a deterministic machine, then everything that happens has a reason that could, in principle, be uncovered. Misfortune is not arbitrary, it is complicated. Randomness is not fundamental. It is a label we use when we have not measured enough details. Think of a pair of dice tumbling across a table. In everyday language, the outcome is random. You speak of luck, chance, good or bad rolls. But in a classical world, that randomness is only apparent. If you knew the exact way your fingers pushed the dice, the tiny irregularities in their shape, the air currents in the room, the hardness of the table, you could, at least in principle, calculate which faces would land upward. The unpredictability you experience is a measure of your limited access to information, not a feature of the universe itself. At the scale of planets and projectiles, this outlook works extremely well. Using Newton's laws of motion and gravity, astronomers predicted eclipses, the return of comets, the existence of previously unseen planets whose gravitational pull betrayed them. Engineers built bridges and machines with confidence that forces would add and balance in ways they could foresee. When something failed, the search was for a missing factor, not for a breakdown of causality. This alignment between theory and experience had a subtle psychological effect. It encouraged a way of living in which the world could be trusted to behave, even when it did not behave kindly. Storms, accidents, illnesses could be traced back to chains of events. If those chains were long and intricate, that was a practical inconvenience, not a philosophical wound. Somewhere, behind the scenes, the machinery remained intact. There is a comfort in imagining yourself inside such a universe. To walk through a deterministic world is to move through a landscape where nothing truly comes from nowhere. Even your own choices could, in principle, be understood as the result of earlier states of your brain and body, themselves shaped by genes and environments, by prior causes stretching back before you were born. You may not like the implications, but they are at least coherent. You are not adrift in a sea of uncaused events. Of course, people rarely live as if everything were predetermined. In daily life, you blend two languages without noticing. When you think about the fall of an apple or the orbits of planets, you allow classical causality to rule. When you think about your future, you speak of possibilities, options, forks in the road. The classical picture of the world offers a background against which those subjective experiences unfold. A reminder that, beneath your sense of openness, there might still be a fixed trajectory. The very structure of classical physics encourages this layering. Its equations are time reversible. If you know the present state of a system, you can, in principle, run the laws forward to predict the future or backward to reconstruct the past. The universe becomes a film that can be played in either direction without inconsistency. There is no special moment when reality is decided. There is only a continuous unfolding. When randomness does enter classical discussions, it usually does so through statistics. In thermodynamics and statistical mechanics, for example, physicists describe the behavior of gases not by chasing each molecule individually, but by talking about averages, temperatures, pressures. Yet the underlying belief remains: each molecule still has a definite position and velocity. The statistics are a shortcut, a concession to our limited patience and capacity, not a statement about the fundamental nature of the world. This way of thinking about unpredictability as mere ignorance extends easily into everyday judgments. When you say someone is unpredictable, you rarely mean that their actions are born from true indeterminacy. You mean that you do not have enough information about their motives, their habits, the pressures on them. Given enough insight, you imagine you could have seen their choices coming. It is the same classical instinct, turned inward, but there is another side to this dream of perfect predictability. If everything in the universe follows from earlier states according to fixed laws, then the space left for genuine novelty seems to shrink. Any moment you are alive, in this view, is the result of conditions you did not choose, plus laws you did not write. Your sense of standing at a crossroads may be only a perspective from inside a path that was always going to be taken. Classical physics itself does not tell you what to do with that thought. It does not speak about meaning or purpose. It simply offers a framework in which the state of the world at one time fully determines its state at all other times. Whether that is liberating or suffocating depends on what you hoped the universe would be like. For a while, this did not feel like a problem. The success of classical theories bred a quiet confidence that, with enough refinement, they could eventually account for everything from the motion of galaxies to the behavior of heat and light. The remaining puzzles were seen as technical, not foundational. If a phenomenon resisted explanation, the assumption was that either the laws were being applied incorrectly or some relevant detail had not yet been measured. That is part of why the quantum revolution was so disruptive. It did more than tweak equations. It challenged the very idea that the future is, in principle, fully written into the present, available to any hypothetical intelligence that knows enough. It suggested that even if you had complete information about a system according to the theory, you could still only predict probabilities for certain outcomes. Seen from the vantage point of today, the classical worldview has the feeling of a story told in bright daylight. Objects are where they seem to be. Causes lead to effects in continuous chains. If something is uncertain, it is because we have not yet looked closely enough. Behind that, quantum mechanics whispers a different story, in which the act of looking may itself play a role in what can be said to exist. Yet even knowing that, we continue to lean on classical intuition. It shapes the way we plan, the way we assign responsibility, the way we imagine history. We rarely think in terms of wave functions or probability amplitudes when we cross a street or make a promise. We think in terms of trajectories, impacts, consequences. In that sense, the dream of perfect predictability has not vanished. It has become a background assumption, a quiet scaffolding for our sense that the world is out there, solid, following its own path, whether or not we are paying attention. What quantum mechanics does, slowly and uneasily, is to ask how much of that scaffolding we are allowed to keep. It is a strange feeling when the scaffolding you trusted most turns out to be the part that moves. In the classical picture, probability was a temporary concession. You used it when you lacked details, when tracking every molecule of air or grain of dust was impractical. Underneath the statistics, people believed. There was always a definite story, each particle with a position, each object with a trajectory, each outcome fixed in advance by its causes. Ignorance was on our side of the equation, never on nature's. Quantum mechanics did not immediately challenge that comfort. At first, it arrived as a set of successful recipes. Write down a wave function. Let it evolve smoothly according to Schrödinger's equation. Then, when you perform a measurement, use a separate rule to turn that wave into probabilities for different outcomes. That last step, formalized by Max Born in the 1920s and now called the Born rule, says that the likelihood of finding a particle at some place is proportional to the square of the wave function's amplitude there from a distance. That might sound like a familiar use of probability. You have a function that encodes what you know. You use it to compute a distribution of possible results. But there is an important difference. In quantum theory, the wave function is not just a summary of incomplete information about a more detailed reality underneath. As far as the theory itself is concerned, it is the complete description. There is nothing more precise hiding behind it that the equations tell you how to reach. You can see the consequences in one of the most famous experiments in physics. Send particles, one at a time, toward a barrier with two narrow openings, and let them land on a screen behind. When both openings are available and you do not attempt to track which path each particle takes, the pattern that slowly builds up on the screen shows interference fringes, bright and dark bands that reveal a wave-like structure. When you change the setup and obtain which path information, the interference disappears. The statistics of the hits on the screen change in a way that cannot be understood if each particle simply followed a single, definite path all along. The unsettling part is not only the pattern, it is the way it emerges. Each particle arrives as a single detection event, a dot at a particular place. You cannot predict in advance, even in principle, where the next dot will land. You can only predict the overall distribution once many events have accumulated. The wave function, through the Born rule, tells you that the probability is higher in some regions and lower in others. It does not tell you which specific outcome will be realized on any given run. In a classical world, you might respond by saying there must be hidden details we are not including. Perhaps if we knew the precise initial condition of each particle, its internal variables, the state of the apparatus in full microscopic detail, we would find that the seeming randomness is just ignorance. The probabilities would then be like weather forecasts, a practical necessity, not a statement about reality itself. Albert Einstein hoped for something like that. In Letters to Max Born, he complained that the new theory, for all its success, did not bring us closer to the secret of the old one, and expressed his conviction that whatever underlies physics does not play dice. For him, probability at the deepest level felt like an admission of defeat, a sign that the theory was not yet telling the full story. He imagined that a more complete description, with additional variables, would someday restore determinism. That hope faced a major obstacle in the 1960s, when John Bell examined what any such hidden variable theory would have to look like if it respected a basic classical intuition that influences cannot travel faster than light, and that what happens here cannot instantly depend on choices made far away. Bell showed that for a wide class of these local hidden variable theories, the correlations between measurements on entangled particles must obey certain inequalities. Quantum mechanics predicts violations of those inequalities. When experiments were carried out, beginning in the early 1970s and refined many times since, the results matched the quantum predictions and violated the Bell inequalities. No matter how carefully the tests were designed, the data refused to fit into a picture where outcomes are fixed in advance by local hidden properties. If there are hidden variables, they cannot behave in the way classical intuitions about locality demand. Bell's work does not prove that randomness is the only possible way to understand quantum probabilities, but it does close off a large area of conceptual escape. It forces a choice. Either we accept that probabilities are, in some sense, an irreducible part of how the world presents itself to us, or we accept other departures from classical thinking, such as non-local connections or multiple coexisting branches of reality, each with its own realized outcome. None of those options restores the old simplicity. In practice, most working physicists take a pragmatic view. They use the Born rule as a reliable tool. Prepare the system in a certain state, represented by a wave function. Evolve it according to the deterministic part of the theory. When you measure an observable, use the squared amplitudes to assign probabilities to the possible results. Check those predictions against experiments. They work. They keep working. The temptation is to stop asking what. If anything, the probabilities are about beyond that. Yet it is difficult, as a human being, not to ask. In quantum mechanics, even absolute certainty takes a different form from the classical one. If a system is in an eigenstate of an observable, the theory says that a measurement of that observable will yield a particular value with probability 1. But that certainty is conditional. It depends on the way you choose to measure. Ask a different question of the same system, and you are back to a spread of possible results. That dependence on the question is not just a psychological artifact. It is encoded in the non-commuting structure of quantum observables. Measure one property sharply, and the theory tells you that the spread in a complementary property must widen. The uncertainty relations are not statements about the clumsiness of our instruments. They are statements about what kinds of joint definiteness the world will allow. This is where probability stops looking like a placeholder for ignorance and starts looking more like a feature of the landscape. Even if you knew everything the theory allows you to know about a given system, there would still be experiments whose outcomes you could not predict individually, only statistically. The limit is not in your patience or in your ingenuity. It is in the way the formalism ties preparation, evolution, and measurement together. There is a quiet psychological cost to absorbing that. We often live as if the world is a sequence of facts waiting to be discovered, each one fixed and specific, long before we stumble across it. Quantum mechanics suggests a different mood. It whispers that some of what you encounter may not have had a single, determinate value before the interaction that brought it into your experience. The probabilities you calculate are not just about your ignorance. They are about how often the world, when asked the same question in the same way, gives the same kind of reply. It is possible to push back against that suggestion by adopting an interpretation in which the underlying evolution of the wave function remains fully deterministic. In some views, every possible outcome of a quantum process occurs, each in its own branch of reality, and probabilities arise as a way of talking about how likely you are to find yourself in one branch rather than another. In others, additional variables guide the apparent randomness, at the price of accepting non-local influences that knit distant events together. But whatever philosophical path you choose, you cannot return to the classical comfort where randomness is clearly and only ignorance about hidden details in a local, single-path world. At the human scale, we are used to holding a double attitude toward uncertainty. We navigate daily risks with statistics and intuition, treating probabilities as tools for decision-making. At the same time, we nurse an unspoken belief that each event, once it has happened, could in principle be traced back through a chain of causes to a set of determinate beginnings. Quantum mechanics complicates even that quiet afterthought. It tells us that, for some microscopic events that helped shape the present, there may be no finer-grained story available than a list of chances and an actual outcome. Of course, this does not mean everything is chaos. Quantum theory itself is a highly structured framework. The evolution of the wave function between measurements is as rigidly determined as any classical motion. The probabilities assigned by the Born rule are not arbitrary. They are fixed by the state and the observable in a precise way. There is a reliable pattern to the unpredictability. If you repeat an experiment many times, the relative frequencies of outcomes will settle down near the probabilities the theory assigns. The randomness is constrained, disciplined, almost sculpted. But it remains randomness in a sense that troubled earlier generations. Einstein's discomfort was not just intellectual pride. It came from a deep attachment to the idea that the universe, at its core, is lawful in a way that leaves no room for genuine chance. The ongoing experimental confirmation of quantum predictions has not erased that longing. It has only made it harder to satisfy without reshaping what we mean by lawful. Gaitas grease-strained dairas. Late at night, when the world is quiet and your attention narrows to the circle of light around you, it is easy to feel a similar tension in smaller ways. You look back at the path that brought you here and see a sequence of decisions, accidents, opportunities taken or missed. It is tempting to imagine that, with more knowledge, you could have predicted it all. Quantum mechanics does not reach into your biography to rearrange its meaning, but it does place, at the base of physical reality, a reminder that not every event can be forced into the mold of "it had to be this way." I found a believo. The quantum break is not that determinism has vanished completely. It is that probability has moved from the edges of our descriptions to their center. It is no longer only a measure of ignorance about an underlying classical world. It is part of how the world is presented to us when we probe it as precisely as we know how. To recognize that is to accept that some of our oldest intuitions about certainty, causality, and prediction were tuned for a different kind of universe than the one the equations now describe. And from here on, whenever we talk about observation, measurement, or information in quantum theory. That shift will follow us. The dice, whether you like them or not, are built into the rules of the game. But dice only matter when someone lifts the cup, lets them fall, and dares to look at the faces that land upward. In quantum mechanics, that simple act of looking is no longer a neutral gesture. It is not a passive gaze cast onto an already finished world. It is an interaction, a coupling, a physical event that forces the quantum description to give you one concrete answer and, in doing so, seems to erase all the other answers that might have been. We usually call it a measurement. The word sounds technical, but the idea is simple. You arrange a device so that the microscopic system leaves a mark you can read. A flash in a detector, a click in an earpiece, a dot on a screen. Before that interaction, the system is described by a wave function that spreads its possibilities across space, across different outcomes. Afterward, only one outcome shows up on your record. In the equations, this difference is dramatic. Between measurements, the wave function evolves smoothly and deterministically, like a calm river following its bed. At the moment of observation, that smooth evolution is replaced by a sudden jump. The wave function collapses into a single branch compatible with the result you actually see. There is no gradual narrowing, no continuous squeezing of uncertainty into certainty. There is just a before and an after. The trouble is that the theory itself does not tell you exactly when or how this jump occurs. It tells you how to compute the probabilities of different outcomes. It tells you how the wave function flows between observations, but it does not specify a clear physical threshold where unobserved evolution becomes observed event. Somewhere between the electron and your awareness, something happens that the standard formalism describes only as a rule. After you read the result, update the wave function accordingly. Take the double-slit experiment again. But this time, imagine adding a tiny detector near one of the slits, capable of registering whether the particle passes by. When the detector is off, you find an interference pattern, a set of fringes that suggest each particle behaves like a wave, exploring both paths. When the detector is turned on and actually records which slit the particle used, those fringes disappear. The distribution on the screen changes. It now looks like the result you would get from classical particles, that each went through only one opening. Nothing in the physical layout of the slits themselves has changed. The barrier is the same. The screen is the same. The only difference is that you have introduced an interaction strong enough to leave a which path mark in the environment. The presence or absence of that information determines whether interference shows up. It is as if reality will allow certain patterns only when no one, and nothing, has obtained knowledge that would contradict them. This is very different from classical measurement. In classical physics, you can, at least in principle, measure gently. You can imagine taking the limit where your instruments disturb the system less and less, approaching a situation where observation simply reveals what is already there. In quantum mechanics, the disturbance is not something you can remove entirely. It is woven into the structure of the theory. Asking certain kinds of questions in certain ways changes what future questions can be meaningfully asked. Physicists sometimes illustrate this with thought experiments that stretch the idea of observation. Picture a sealed laboratory where an experimenter measures a quantum system, records a result, and perhaps even says it aloud. Outside the lab, another observer treats the entire laboratory, the apparatus, the experimenter, the recorded data as one big quantum system, still described by a superposition of different possible outcomes. From inside, the experimenter experiences a definite result. From outside, the larger description has not yet collapsed. The line between measured and not yet measured blurs. If that makes you uneasy, you are not alone. The measurement problem is not a minor technical issue. It is a tension between the two ways the theory tells us the world changes, continuous evolution for closed systems and abrupt jumps at observation. Where one process hands off to the other is left vague. Different interpretations of quantum mechanics draw that line in different places, or erase it in different ways. But the underlying fact remains: the act of observing cannot be treated as a passive window onto a fully formed reality. It would be easy, at this point, to slip into stories about consciousness shaping the world, about minds creating reality. The mathematics does not require that. Quantum measurements can be understood in terms of interactions with any sufficiently complex environment, regardless of whether a conscious observer is involved. A photon bouncing off an atom, a particle leaving a track in a cloud chamber, an electron transferring its energy to a pixel on a sensor. These are all observations in the physical sense. They are all ways in which a spread of possibilities becomes, for practical purposes, a single recorded fact. Yet there is still something personally disorienting about this. We are used to thinking of ourselves as spectators who step into a pre-written universe, watching events unfold. Quantum mechanics hints that every observation you make is also a small act of selection, not a free choice of outcome, but a narrowing, a pruning of branches, a commitment to this result rather than that one, this history rather than another. None of that is under your voluntary control. You cannot decide, by wishing, which way a radioactive atom will decay or where a photon will land. But you participate simply by being part of the chain through which those events are registered. Your detectors, your nerves, your memories become sites where possibilities end and specific experiences begin. The world that feels solid to you is the one that has passed through those transitions. Look again at the simple idea of a trajectory. In classical physics, a particle has a path through space that exists, whether or not anyone reconstructs it. You can, if you like. Imagine that path as a thin line, always there. In quantum theory, before measurement, the wave function does not say, the particle is secretly following this one track. It says, here is a structured cloud of potential locations, each with its own amplitude. The notion of a single line appears only when you force the system into leaving a detectable trace. And once that trace exists, there is no way to erase it completely. You can scramble it, hide it, bury it under new data. But the fact that a particular outcome occurred has entered the shared history of the system and its environment. From that point on, all future probabilities are conditioned on that past. What was once a range of options has become a single starting point. You live at the end of countless such branchings, many of them microscopic and unnoticed, their cumulative effect forming the macroscopic reality you call your life. Delayed choice experiments push this logic further. You can set up a situation where the decision to preserve or destroy interference is made after the particle has already passed the slits, or after its entangled partner has been detected elsewhere. The statistics of the outcomes still fall into line with whichever measurement you eventually perform. It is tempting to say that the particle must have known what you would decide, or that the future somehow reached back to change the past. The more careful conclusion is that the quantum description refuses to assign a single, definite story about what really happened between emission and detection, unless the whole experimental context is taken into account. From a certain angle, that looks like a direct challenge to the instinct that the world exists in full detail, whether or not anyone probes it. Objectively, something is happening all along. The particles do not vanish into nothing between interactions, but the structure we usually demand a list of properties that are always either this or that does not easily apply when no measurement pins them down. The theory stays silent on questions it was not asked in the right way. Living with that silence is not easy. Every part of your day teaches you to trust that things have definite states at all times. The book is either on the table or not. The light is either on or off. You are either here or elsewhere. Quantum mechanics does not deny these everyday certainties at the scales where they work. It suggests that, underneath, the transition from many possibilities to one actuality is more subtle than our language allows, and more tightly bound to acts of interaction than we might like. It is important to note what this does not mean. It does not mean that reality depends on your personal attention in order to exist. Galaxies formed long before there were human eyes to see them. Radioactive atoms decayed in rocks and stars for eons before anyone built a detector. What quantum theory does say is that the specific outcomes we count as facts are always tied to physical processes that record them. The universe is full of such processes: dust grains, gas clouds, planets, and fields are constantly interacting, constantly leaving traces in one another. From that wider perspective, observation is not a special privilege of brains. It is a general feature of interactions in a quantum world. Whenever two systems become correlated in the right way, information about one is imprinted on the other. The vast majority of these imprints never reach any conscious mind. They are written in patterns of scattered photons, in vibrations of matter. In the relentless bookkeeping the universe seems to do about itself. Still, for each of us, the most immediate version of this is personal. Your memories are a record of interactions. You do not remember superpositions. You remember definite events, a word spoken, a door closing, a particular face in a particular light. What quantum mechanics quietly tells you is that, at some earlier stage, there were situations in which several such outcomes were all live possibilities in the wave function. The moment you recall is one thread drawn from a tangle that the formalism never forces into a single path until something like a measurement occurs. This is unnerving, not because it makes you unimportant, but because it places you squarely inside a universe where certainty is fragile. Every observation you make, every reading on every instrument, is an island of definiteness in a wider sea of potential. You navigate by those islands. You build scientific theories from them. You base your personal story on them. Yet the theories themselves point back to a level where definiteness is not automatic, where it has to be earned through interaction. By now, people have proposed many ways to soften this picture. Some emphasize the role of large environments in making certain outcomes effectively irreversible, so that what once was a delicate superposition becomes, for all practical purposes, a classical fact. Others treat the wave function as a tool for managing expectations rather than a literal description of the world. Still, others accept that there may be parallel branches where different outcomes occur, though none of those branches ever reunite for comparison. All of these responses change how we talk about observation. None of them quite restore the old comfort of a world that exists fully formed in the same way, whether or not it is ever measured. The act of observing remains a hinge in the story, a place where the language of quantum amplitudes gives way to the language of definite results. If you listen closely, there is a quieter question beneath the technical debates. How much of what you take to be the world is, in fact, a record of interactions that happen to include you? How much of reality, as it matters to a finite observer on a small planet, is a history of choices made by measuring apparatus, by atoms, by eyes, long after the underlying wave functions have already moved on? Quantum mechanics does not answer that question. It does not tell you what reality is when absolutely no one, and nothing, is there to give it a shape. It tells you how to predict the statistics of the shapes that do appear. When systems meet and leave traces in one another, it tells you that observation is not an afterthought, but part of how the world you know comes into being. And perhaps that is the most unsettling part. Not that everything depends on you, but that what you call everything might only be the thin, observed edge of something that does not easily fit into the stories you tell, about solid objects marching along fixed paths, indifferent to whether anyone is watching. If what you call reality is the thin, observed edge of something larger, then superposition is the name we give to the part that does not usually make it into your story. At first glance, the word sounds technical and distant, but the idea it carries is simple and deeply uncomfortable. In our everyday language, something is this or that, here or there, true or false. The structure of sentences mirrors the structure we expect the world to have. Superposition says, at the quantum level, before the right kind of interaction forces a decision, that either-or logic does not always apply. In the formal language of quantum mechanics, a system is described by a state. If you choose one property to focus on, say, the position of a particle, or the orientation of its spin, you can list the different outcomes a measurement might reveal. Each outcome corresponds to a basic state. A superposition is not a situation where the system is secretly in one of those states, and you just do not know which. It is a combination of them all at once, with weights called amplitudes that carry both size and phase. An ordinary coin gives you a familiar reference point. When it lands, it is either heads or tails. If you do not look, you may say you are in doubt, but the coin itself is not. It has a definite orientation long before you check. Your uncertainty lives only in your mind. A quantum superposition is not like that. It is not a description of your ignorance about a definite hidden face. It is more like a coin that has been set into a state which, according to the theory, genuinely does not count as only heads or only tails until a measurement forces the issue. The double-slit experiment shows this in a particularly sharp way. Imagine sending single particles toward a barrier with two narrow openings. If you block one opening and leave the other open, the pattern that builds up on the screen behind is what you would expect from particles traveling along a single path. If you open both, but arrange things so that no information about which path any given particle takes is recorded anywhere, the pattern slowly transforms into something very different. Bands of high and low detection probabilities that reveal underlying wave-like interference. We are tempted to say that each particle really went through one slit or the other, and that the interference pattern is just a statistical mirage built from many such hidden choices. The mathematics and the experiments resist that story. The superposition that passes through the barrier is a single state that involves both paths at once. The interference arises from the way the amplitudes associated with those paths combine, not from ignorance about which one was taken. When you try to force the world back into the old categories by installing detectors that mark which slit each particle uses, the interference disappears. The distribution on the screen shifts back to something more like the sum of two independent streams. It is not that the particles suddenly become more classical out of modesty when watched. It is that the act of recording which path they took destroys the delicate phase relationship between the components of the superposition. The state changes from a coherent both into a mixture of either that no longer produces fringes. This distinction between a coherent superposition and a mere mixture matters. In a mixture, the system is in one of several definite states, and you simply do not know which. In a superposition, the system is in a genuinely combined state that can produce interference effects when the components are allowed to overlap again. That interference is the signature that something deeper than classical uncertainty is at work. For simple systems, such as an electron's spin, you can see this structure clearly. Prepare the electron so that its spin is aligned along one direction. In that configuration, a measurement along that same direction will always give the same result. But if you change the orientation of your measuring device, the very same electron is now described as a superposition of up and down relative to the new axis. Repeat the experiment many times, and you will see a distribution of outcomes. Change the angle and the proportions change. The probabilities are determined by the geometry of the state space, not by a hidden list of pre-written answers. It might be tempting to think that superposition is an artifact that only shows up for very small, simple particles. but experiments have demonstrated interference for much larger systems. Beams of molecules built from 60 carbon atoms, structures sometimes compared to tiny soccer balls, have been sent through carefully constructed gratings and shown to produce interference patterns, revealing that their center of mass motion can be placed in quantum superposition as well. Even more strikingly, superconducting loops containing countless electrons have been engineered so that currents circulate clockwise and anti-clockwise at the same time, forming the basis of devices known as flux qubits. These systems behave as if they occupy superpositions of two macroscopically distinct states, until interactions with their environment or a measurement causes one outcome to be registered. The point is not that cats in boxes or chairs in rooms literally sit in visible superpositions in any everyday sense. The point is that the same mathematical structure that describes a photon passing through both slits, or an electron spin being both aligned and anti-aligned relative to one axis, can be extended, in principle and sometimes in practice, to increasingly complex systems. The difference between quantum strangeness and classical familiarity seems to be less about a magical size threshold and more about how quickly and thoroughly a system becomes entangled with its surroundings. That entanglement is what, in later language, will be described as decoherence. A superposition that involves just a few degrees of freedom in isolation can produce interference. Once it becomes entangled with a vast environment, air molecules, photons, vibrations in a solid, the relative phases between its components become inaccessible in practice. The system still obeys quantum rules, but from your limited vantage point it behaves as if one outcome has been selected and the others discarded. There is a quiet lesson hiding there about the kinds of questions we habitually ask. We like to demand that, at every moment, every system have definite properties, whether or not anyone could, even in principle, check them. Quantum superposition suggests that this demand may be more about our preferences than about the world. In many situations, there is no fact of the matter about which of several alternatives is really true until some interaction brings that alternative into the web of recorded events. You can resist that conclusion by insisting that, underneath the wave function, there is a more detailed layer of reality in which each particle always has a specific position and momentum. Each current always flows in one definite direction. That is one path pursued by some hidden variable theories. But as we saw earlier, maintaining that picture while respecting constraints like locality requires paying a price elsewhere. And even in those frameworks, the operational predictions of superposition, the interference patterns, the statistics of measurement outcomes are the same. Whatever is happening beneath, the world behaves. For all tests so far, as if superpositions are real features of its description. There is something quietly familiar in that. If you shift your attention from physics to life, before you make a significant decision, your future seems open in several directions. You can imagine different versions of yourself, each following a different path. Those imagined futures coexist in your mind for a while. Once you act, one of them becomes the story you actually live, and the others recede into something harder to name. Of course, this is only a metaphor. Your choices are not governed by quantum amplitudes in any straightforward way. But the structure is suggestive, multiple possibilities held together, then narrowed into one experienced branch. Quantum superposition does not claim that all possibilities are equally real in a human sense. It does not grant personal meaning to every term in an equation. What it does is force us to admit that the world, at the level where our best-tested theories operate, does not always honor the crisp boundaries we draw between alternatives. Sometimes, the most accurate description we have is not this or that, but a state that, if interrogated in this way, will sometimes behave like this, and sometimes like that, with a pattern of outcomes that only the superposed structure can explain. I was, late at night, when your attention is no longer pulled outward by constant demands. It can be disorienting to realize that much of what you take for granted as a single, stable reality is built atop layers of such unresolved structure. The objects in your room feel unequivocal. The memories in your head feel like a single continuous line, but the atoms that compose them have spent most of their existence in states that, if described with full honesty, would involve many simultaneous possibilities, pruned only when interactions forced them into sharper roles. None of this means you are somehow living several lives at once in any literal sense. It means that the intuition which says, at every moment, everything must be exactly one thing or another, fully specified in a way that mirrors my language, is a convenience, not a law. Superposition is the reminder built into the equations that nature's bookkeeping does not always align with the categories that feel safest to us. And still, we function. You reach for a glass and do not worry that your hand is in a superposition of many positions until it touches it. You walk through a doorway and do not imagine yourself spread across both sides. The quantum structure recedes under the weight of countless interactions with the environment, giving rise to the robust classical world you trust. That world is not an illusion, it is an emergent pattern, a zone where superpositions have become so entangled with surrounding degrees of freedom that, for all practical purposes, only one outcome remains visible. The discomfort comes from knowing that this robustness is not absolute. It has conditions. It depends on scales and couplings, on how quickly information leaks out into the environment, in carefully isolated systems, in laboratories cooled and shielded from noise. Superposition can be preserved and manipulated over times long enough to perform computations, to store information, to test new facets of the theory. In those places, the underlying quantum structure declares itself openly. Everywhere else, it stays quiet, hidden beneath the illusion of single-valued facts extended through time. Quantum mechanics does not command you to discard that illusion in your daily life. It simply suggests that, when you peel back enough layers, the language of many things at once becomes unavoidable. The world does not always respect the tidy lines we draw around identities and alternatives. It allows combinations we do not see directly, but whose traces show up in the interference patterns, in the stability of atoms, in the behavior of devices built with precise control over microscopic states. In that sense, superposition is less a magic trick and more a statement of humility. It is a reminder that your favorite way of carving up reality into sharp, exclusive options is one possible description, among others, valid in the regime where interactions have already done the work of selection. Beneath that, whenever you try to describe what exists before it is forced to answer, you are dealing with a structure that does not quite fit into any of the simple boxes that language offers. Time is where that hidden quantum structure stops being an abstract idea and quietly starts running your day. Because without it, even the simple feeling that a second is a second would have nothing solid to sit on. In school, time is presented as a smooth line. Seconds, minutes, hours, marching forward in even steps, like marks on a ruler. Ordinary clocks try to mimic that, a pendulum swinging, a quartz crystal vibrating, gears turning. But none of those are truly fundamental. They drift. They age. They respond to temperature, gravity, wear. They are stories we tell about time using moving parts. Physics eventually had to ask a sharper question. If time is something we measure, what exactly is our best clock? What process in the universe is so regular, so stable, that we can build all other rhythms on top of it? The answer did not come from swinging masses or planetary orbits. It came from quantum mechanics, from the way atoms absorb and emit light. Each kind of atom has allowed energy levels for its electrons, like rungs on a very specific ladder. Electrons do not slide smoothly between rungs. They jump. When an electron falls from a higher energy level to a lower one, it emits a photon, whose frequency is set by the energy gap. That gap, for a given transition in a given kind of atom, is not negotiable. It is dictated by the quantum structure of that atom, which is the same in every laboratory, on every continent, in every corner of the universe where the conditions are similar. The cesium atom, with its particular internal structure, turned out to be especially useful. In the late 1960s, international metrology organizations decided to define the base unit of time not by the motion of the Earth, but by a specific microwave transition between two hyperfine levels in the ground state of cesium-133. 1 second is now defined as the duration of exactly a fixed number of oscillations of that radiation, 9,192,631,770 cycles. That number is not chosen for poetry. It is chosen because it matches, as closely as possible, the length of the second, inherited from astronomical definitions, while tying it to something atoms can reproduce with astonishing reliability. When you speak of a second today, you are referring, whether you realize it or not, to a count of quantum oscillations in a cloud of cesium atoms, somewhere in a national standards laboratory. In an atomic clock, those atoms are coaxed into a superposition of the two hyperfine levels. A microwave field drives transitions between them. When the frequency of that field is tuned just right, the atoms respond maximally, flipping between their internal states in a kind of quiet resonance. The clock's electronics continually adjust the microwave source to stay locked to that resonance, using the atoms themselves as a reference. Time, in this picture, is no longer a vague flowing background. It is the phase of a quantum state, ticking forward as the superposition evolves. Modern cesium fountain clocks refine this idea. Atoms are cooled to near absolute zero and tossed upward in a fountain-like trajectory inside a vacuum chamber. As they rise and fall, they interact with carefully controlled microwave fields twice, once on the way up and once on the way down. The interference between these interactions sharpens the measurement of frequency, like a delicate quantum version of listening for beats between tuning forks. With such devices, the uncertainty can be pushed down to around 1 part in 10 to the power 16, which means that if such a clock ran for roughly 100 million years, it would drift by about 1 second. Numbers like that are hard to place next to a human life. Your own sense of time is shaped by heartbeats, breaths, commutes, conversations. To a person, an hour can stretch or shrink depending on how it is filled. To a cesium fountain, an hour is just an accumulation of an enormous, fixed count of identical oscillations. There is no boredom, no anticipation, no narrative, only a phase that advances, steady, indifferent. Yet that indifferent tick organizes much of the world you move through. Global navigation systems rely on satellites, each carrying multiple atomic clocks based on cesium or rubidium. The signals they broadcast include timestamps, and your receiver infers your position from how long those signals took to arrive. A timing error of only about 1 microsecond, 1 millionth of a second, can translate into a position error of roughly 300 meters. To keep your location fixed stable, the system depends on clocks that rarely stray more than a few billionths of a second over a day. So when you glance at a map on your phone and see a small icon marking where you stand, you are looking at the downstream effect of quantum timekeeping. The location is not just a dot on a picture. It is the solution to a problem that can only be solved if many distant clocks circling the planet stay in step, according to a definition of the second, rooted in cesium atoms. Time, in that very literal sense, is how you know where you are. There is a quiet oddity in this. For most of history, time was local. Villages rang bells when the sun was high. Cities kept their own standards. Noon was something you could point at in the sky. Now, noon, in different places is coordinated by systems that listen to quantum transitions in lab equipment and in satellites you will never see. Your daily schedule, your work, your calls, your travel are all threaded through a grid of instants defined far outside your awareness. Quantum mechanics is not just hiding under that infrastructure, it is the infrastructure. Without the stability that comes from discrete energy levels, from the reproducibility of transitions in identical atoms, there would be no way to maintain such precise synchronization over long periods. Pendulum clocks and mechanical devices might keep rough order, but they would not be able to support global networks that require nanosecond-level agreement. At the same time, relativity quietly complicates the picture. Time does not flow at exactly the same rate everywhere. It depends on how fast you are moving and how deep you sit in a gravitational field. The clocks on satellites tick slightly faster than clocks on the ground because they are higher in Earth's gravity well and moving differently in orbit. Their readings have to be corrected using general relativity before your receiver can make sense of them. The combined effect is tiny in human terms and crucial in technological one. So at the heart of the modern world is a compromise between quantum discreteness and relativistic flexibility. The base unit of time is defined using a quantum transition in a specific atom. The way that unit unfolds in different places depends on the curvature of spacetime. National laboratories compare their clocks, average them, and publish a consensus timescale. The seconds on your wrist, on your screen, on the network, are all tied back to that invisible, negotiated foundation. There is a kind of quiet estrangement in realizing this. The time you feel the sense of a day being long or short, a year rushing past or dragging, is not the same as the time your devices keep. For them, a second is a fixed count of cesium oscillations. For you, a second can expand in fear, compress in joy, vanish altogether in sleep. You live in two overlapping temporal worlds, one defined by quantum transitions and equations, the other by experience and memory. Quantum timekeeping does not resolve that tension. It sharpens it. It shows how far you are willing to go to make the world predictable, to coordinate billions of lives through a shared standard that does not care about any of those lives individually. Each tick of an atomic clock is identical. Each tick of your own awareness is not. Between those two kinds of time, you build a life that has to respect both schedules at once. Still, there is a certain humility in knowing that the now in which you sit is indexed, in part, to processes that continue whether or not any person thinks about them. Clouds of atoms in shielded rooms shift between internal states. Lasers interrogate them. Electronics record the results. Satellite clocks broadcast their readings into space. Algorithms pull all of this into a global time signal. You check the hour, see that you are late or early, and act. In that sense, quantum time is both distant and intimate. Distant, because it takes place in regimes of precision and control that most of us never encounter directly. Intimate, because it seeps into the smallest routines, waking up to an alarm, catching a train, joining a call scheduled across continents. Each of those is anchored to a definition of a second that lives. Ultimately, in the abstract space of quantum states and transitions, if you strip away the technology and look at the structure underneath, what remains is an idea that time, as we use it, can be grounded in the regularity of microscopic systems, even if those systems themselves are described by a theory that treats certainty with suspicion and probability as essential. The smooth line of classical time, the simple ticking of a wall clock, turns out to rest on the trembling of atoms in superposition, on oscillations counted with care, on a quantum rhythm that never quite matches the way time feels from the inside. If time at the quantum level already fails to match the way it feels from the inside, optical clocks take that mismatch and turn it into an instrument. Microwave clocks built on cesium are good enough to govern a planet, But physics rarely stops at good enough. The next step was to ask a simple question with difficult engineering attached to it. What if we built clocks from faster light? Cesium standards count the rhythm of a microwave transition, where the electromagnetic wave is relatively slow. Optical clocks use visible or near-visible light, whose frequency is higher by roughly 100,000 times. That means that in the same slice of time you once marked with microwaves, an optical clock can count vastly more ticks. More ticks mean finer resolution. The second does not change. But what you can see happening inside it does. To make use of that, you need atoms with narrow, well-defined optical transitions, electrons that can sit in two specific energy levels whose gap corresponds to a color of light a stable laser can reach. Strontium has such a transition. So do elements like ytterbium, aluminum ions, and others. In an optical lattice clock, thousands of strontium atoms are held almost motionless in a grid of light, like marbles pinned in the wells of an egg carton made from standing waves. Each atom becomes a tiny pendulum, not swinging in space, but oscillating in the relative phase between two internal states. A laser, stabilized with extraordinary care, interrogates that transition. If its frequency is exactly right, it drives the atoms into a superposition that evolves in time with a predictable phase. If the laser drifts, the pattern of absorption and emission shifts, and feedback circuits pull it back. The atoms are not just passengers in this process. They are the reference. The result is a family of clocks whose fractional uncertainties reach into the range of a few parts in 10 to the power of -18 and below, far surpassing cesium fountains. Put into terms closer to a human timeline, some of the best optical clocks now being demonstrated would, if they could run undisturbed, drift by about a single second over tens of billions of years. On the order of 30 to 40 billion, the age of the universe, by comparison, is less than half that span. It is hard to hold that in your head. You will not be here in a billion years, let alone tens of billions. No civilization, you know, is likely to last that long. Yet we are building devices whose imagined performance is measured on those scales. As if we could stand outside cosmic history and demand that even then, the seconds line up. What makes these clocks more than technical trophies is what they do to space itself. According to general relativity, time does not pass at the same rate everywhere. Clocks deeper in a gravitational field tick more slowly than clocks higher up. For a long while, this was a prediction best illustrated with thought experiments about twins and fast rockets. With optical clocks, it becomes something you can test over distances measured in the width of your hand. In one series of experiments, teams using strontium optical lattice clocks compared the tick rates of atoms confined at slightly different heights. They found that clocks separated by a vertical distance of just a few tens of centimeters, roughly the span from the floor to your knee, ran at measurably different speeds, in precise agreement with Einstein's equations. In later refinements, even separations on the scale of a millimeter began to reveal detectable differences. At that point, time dilation stops being a curiosity for space travel and becomes a feature of the room you are in. The clock on a high shelf, if it were precise enough, would tick ever so slightly faster than the same model on the floor. The top of your head lives in a marginally different rate of time flow than the soles of your feet. The differences are unimaginably small in terms of experience. They are completely real in terms of measurement. Optical clocks turn those tiny differences into something like a map. Because the rate at which a clock ticks depends on gravitational potential, you can use clocks as sensors of height and mass distribution. Place two ultra-precise optical clocks far apart. Link them with fibers or satellite signals, and compare their frequencies. Any persistent shift tells you that the gravitational field at one location is not quite the same as at the other. This idea, sometimes called relativistic geodesy, hints at a future in which changes in the distribution of water, ice, or underground structures might be tracked by watching networks of clocks drift together or apart. The same devices that define the second become instruments that reveal where space-time is stretched or compressed. Timekeeping becomes a way of listening to the shape of the Earth, even to the silent movement of mass beneath the surface. There is something quietly unsettling about that. You grew up, most likely, with a picture of time as the same everywhere, a shared river in which everyone floats. These experiments say otherwise. They whisper that each of us carries a slightly different rhythm, set by position and motion, by gravity and speed. When you arrange to meet someone at the same time, you are already brushing aside small physical differences in favor of a shared, humanly convenient fiction. The optical clocks themselves are not bothered by this. They sit in vacuum chambers, bathed in laser light, insulated from noise as much as possible. They do not care why they are being made more precise. They do not ask whether it matters that, at one height, a second is a fraction longer than it is somewhere else. They simply follow the quantum rules, allowing their internal states to evolve as the equations command. From our side, the picture is messier. We need time to be both a universal coordinate and a local condition. We want it to be the same for everyone when we schedule a conversation, yet peculiar enough to bend near black holes and to depend on altitude in laboratories. Optical clocks expose that double wish. They provide moments that are as nearly identical as any we have ever carved out of reality. And then they show us that those moments are not identical after all. Once you pay attention to where they occur, the core of an optical clock is a quantum superposition slowly rotating in an abstract space of phases. When that rotation is mapped onto the ticks of a counter, it becomes time. But the rate of that rotation, as seen from elsewhere, depends on gravity and motion. Time, in this view, is not a backdrop against which events unfold. It is an emergent bookkeeping of how those quantum phases advance in different parts of the universe. When gravity is stronger, the phases advance more slowly. When gravity is weaker, they quicken. If you follow that idea far enough, the boundary between measuring time and measuring space-time dissolves. Every reading on a sufficiently precise clock is also a statement about where the clock sits in the gravitational landscape, about how fast it is moving, about the curvature of the world around it. To read time is to read your place in that curvature. At a human scale, that can be a quietly disorienting thought. You are used to thinking of your life as stretched along a single timeline, shared with others. Optical clocks suggest a slightly different image. Many local threads of time, kept in rough alignment by shared standards and constant communication, but fundamentally tied to where and how each clock, each body, each device exists. The sense of a universal now is, in this picture, a carefully maintained agreement rather than a basic feature of the universe. And yet, in the glow of a late-night screen, the abstraction softens. Somewhere, atoms in a laboratory are cycling through their quantum rhythms, defining seconds more accurately than any heart could ever beat them out. Somewhere else, lasers interrogate ions in a trap, pushing accuracy to more decimal places than you will ever need. Those distant pulses structure the digital world you inhabit, even as your own sense of time stutters and stretches with mood and memory. Optical clocks do not make time less mysterious. They make it more precise and, in doing so, reveal how far that precision is from the way time is actually lived. They show that the universe will let you pin down the length of a second in breathtaking detail, even while refusing to grant you a single, timeless stage on which that second means the same thing everywhere. If time can be read from the trembling of atoms, then lasers are the pens we use to write that trembling into the world. Ordinary light is messy, a filament glows, and countless atoms emit photons in every direction, with a spread of colors. at random phases. It is like a crowd talking all at once in many languages. There is energy there, but little order. Quantum rules are still at work in each emission event, but they are drowned in averages, blurred into something that looks almost classical. A laser begins with the same microscopic ingredients and does something different. It persuades a large collection of atoms or molecules to behave as if they were part of a single conversation. Instead of emitting light at random times and in random directions, they are coaxed into a regimented process where each photon encourages the creation of another, just like it. Out of the same quantum laws that allow chaos, a new kind of order appears. The key is a simple but profound feature of quantum theory called stimulated emission. In the usual spontaneous process, an excited atom eventually falls back to a lower energy state on its own, emitting a photon with a certain energy and phase that are not under anyone's control. In stimulated emission, an incoming photon of just the right frequency interacts with an excited atom and triggers its decay, producing a second photon that is identical to the first in direction, energy, and phase. This is where the ordering begins. If you can create a situation where more atoms sit in the excited state than in the lower state, then an entering photon is more likely to stimulate a copy than to be absorbed. Light passing through such a medium is amplified, but in a very particular way. The outgoing photons line up with the incoming ones. The process repeats. A wave that matches the transition frequency and direction can grow, feeding on the store of excited atoms, while other modes die away, creating that unusual distribution of populations between energy levels. More atoms excited than relaxed is called population inversion. Left alone, systems tend to relax downward. The inversion is a delicate, driven state, held in place by pumping energy in from outside. Electrical discharges in a gas, light from another source, current in a semiconductor. The laser is always a structure out of equilibrium, a balance between pumping and decay. Inside the optical cavity of a typical laser, mirrors send light back and forth through the amplifying medium. Only waves that fit an integer number of half wavelengths between the mirrors are reinforced. All others gradually cancel or leak away. In the end, one or a few modes dominate, producing a beam that is narrow in direction and tightly clustered in frequency. The photons in that beam are not identical in some mystical sense, but they are strongly correlated. They form what physicists call a coherent state. Coherence is what makes lasers so different from light bulbs. A coherent beam can be focused to a tiny spot without smearing out. It can stay narrow over great distances. Its phase is well defined, which means that when two beams meet, the resulting interference pattern is stable and predictable. The randomness of individual emission events does not vanish, but it is channeled into a collective behavior that looks, from afar, like almost perfect regularity. This is, in a quiet way, another example of the tension that runs through quantum physics. At the level of single atoms, emission times are governed by probabilities. You cannot predict exactly when a given excited atom will emit a photon. What you can predict and control is the structure of the ensemble. By designing the energy levels, the pumping mechanisms, and the cavity, you shape the landscape in which those random events occur, so that their average behavior becomes something humanly useful. From an existential distance, there is something familiar about that. You cannot predict individual moments in your own life with precision. Encounters, thoughts, shifts of mood arise from countless causes you will never track, yet patterns still form. Habits, careers, relationships, cultures, they emerge from statistics of many small events, not from a single tight script. A laser is a physical example of how, under the right constraints, a system full of microscopic unpredictability can produce macroscopic order. Technically, lasers have become the rulers of the modern world. not in the sense of power, but in the sense of measurement. Because their frequency is so stable and their waveform so clean, they can be used to compare distances, times, and energies with astonishing precision. Instead of laying a metal bar end to end, you count cycles of light as they bounce between mirrors. Instead of relying on irregular mechanical motion, you trust the disciplined marching of phases in an optical cavity. The same coherence that makes lasers sharp tools also makes them revealing probes. When a laser beam travels through a medium, tiny changes in that medium's properties, its density, its refractive index, the presence of subtle fields can shift the phase of the light. Those shifts are too small to see directly, but when you interfere the beam with a reference, they show up as changes in an interference pattern. The beam becomes a messenger, carrying information about what it has passed through without being completely scrambled by it. This is what allows lasers to measure distances smaller than the width of an atom, to read the microscopic structure of materials, to track vibrations in mirrors and membranes that move by amounts too small to picture. It is also what will later let instruments listen for distortions in spacetime itself, by watching how long it takes light to travel back and forth down long tunnels. If you step back, the story is quietly strange. The quantum theory that first arrived as a way to explain the graininess of energy, the unpredictability of emission, and the statistical nature of measurement, is also the theory that lets us create light with an almost eerie level of predictability. We did not escape the probabilities. We learned how to stack them in our favor. There is an irony in that many people first encounter quantum mechanics as a synonym for uncertainty, for a universe in which nothing can be known fully. Yet our most precise technologies, including the optical clocks we have just met, depend on quantum coherence and quantum control. The same rules that insist some questions cannot have definite answers also allow us to build devices whose behavior is stable, far beyond anything imagined in the age of purely classical machines. Maybe that is why lasers feel, in a quiet way, like an honest symbol of the quantum world. They do not erase randomness. They discipline it. They do not grant us absolute certainty. They let us draw very fine lines in a universe that still refuses to reveal everything. And every time a narrow beam of light traces a straight path through the air, you are seeing, without fanfare, a moment when quantum rules have been coaxed into producing something that looks, for a while, almost perfectly ordered. It is one thing to coax a narrow beam of light into order. It is another to use that beam as a ruler for the quiet stretching of spacetime itself. Far from cities, on flat stretches of land in Washington and Louisiana, stand two instruments that look almost empty. Each one is essentially an L-shaped vacuum system, with each arm stretching for about 4 kilometers, pointing along two directions at right angles. At their meeting point sits the heart of the machine, a laser, beam splitters, mirrors, and sensors arranged into an interferometer designed to measure a change in length so small that, in ordinary terms, it might as well be nothing. The basic idea is conceptually simple. Laser light travels out along both arms, bounces back and forth between mirrors many times, and returns to the central beam splitter. If the arms are exactly equal in length, the returning waves cancel at the output in a carefully arranged pattern of destructive interference, leaving almost no light at the detector. If one arm becomes slightly longer and the other slightly shorter, that cancellation is imperfect. A tiny bit of light leaks through. The detector sees a brief flash, a change in brightness that encodes a change in distance. In practice, the numbers involved are almost absurd. The arms, already several kilometers long, are effectively lengthened further by Fabry-Perot cavities that cause the light to bounce many times between the mirrors, increasing the path over which a gravitational wave can imprint its effect. The strain that LIGO is designed to detect is on the order of 10 to the power of -21, meaning a relative change in length so tiny that the actual motion of the mirrors is far smaller than the diameter of a proton. That sensitivity is not achieved by one trick, but by a stack of them. The laser itself is stabilized at a wavelength of about 1064 nanometers, beginning as a modest seed beam only a few watts strong, and then being amplified until roughly 100 watts of light circulate in the interferometer. The mirrors are polished to extraordinary perfection and suspended on multi-stage pendulums to isolate them from seismic vibrations. The vacuum tubes are among the largest high-vacuum systems ever built, so that air molecules do not scatter the light and spoil the measurement. Even with all of this, the signal from a passing gravitational wave is not something you can see by glancing at a readout. It appears as a tiny pattern buried in noise, a faint rising and falling tone in the data that must be identified with careful analysis. The wave distorts space-time itself, stretching one arm while compressing the other, then reversing, like a passing ripple on a pond. The change in length that corresponds to a detectable event can be as small as around 10 to the power of -19 meters, roughly a billionth of the size of an atom, teased out of an instrument measured in kilometers. For decades, this remained an aspiration. The idea that we might build a device capable of hearing the final moments of black hole mergers or the slow in-spiral of neutron stars felt grand but uncertain. The waves themselves were predicted by Einstein's general relativity, yet he doubted they would ever be measured directly. The distortions they cause are simply too small by the time they cross intergalactic distances and wash through our little patch of space. And then, in the year 2015, the data changed. On a September morning, the two detectors, one in Hanford, one in Livingston, recorded a pattern that looked, to trained eyes, like the brief chirp of two massive black holes spiraling into one another and merging. The signal, lasting only a fraction of a second, swept upward in frequency and amplitude, exactly as models of general relativity had predicted for such a collision. Analysis suggested that the source lay over 1 billion light-years away, in a distant region of the southern sky, and that the merging black holes had masses several tens of times that of our Sun. What reached Earth was a ripple so weak that it altered the effective length of LIGO's arms by an amount equivalent, in proportion, to changing the distance to the nearest star beyond our solar system by roughly the width of a human hair. That almost impossibly small tremor was captured, digitized, compared between sites, filtered, matched against theoretical waveforms, and eventually announced as the first direct detection of gravitational waves. It is easy, when hearing that story, to focus on the spectacle, black holes colliding, space ringing, a century-old prediction confirmed. But there is another, quieter angle. The detection only exists for us as a trace in an instrument, as a tiny modulation in laser light that itself exists, thanks to quantum coherence, in amplifying crystals and carefully polished mirrors. Our ability to listen to the universe in this way depends on technologies that work because we have learned to play within the limits set by quantum mechanics. There is a long chain between the distant event and your awareness of it. Two black holes, once massive stars, orbit closer and closer, radiating energy in the form of gravitational waves. In their final moments, they move at appreciable fractions of the speed of light, twisting space-time so violently that waves ripple outward across the cosmos. Those waves travel for more than 1 billion years, expanding, weakening, yet retaining the imprint of their source. Eventually they pass through Earth, ever so slightly stretching and squeezing the planet. The air, your body, almost all of that motion passes unnoticed, only in the arms of the interferometers, where laser beams race back and forth and interfere. Does the wave leave a record strong enough to survive scrutiny? The data are stored, processed, calibrated. Somewhere, a human being looks at a plot on a screen and realizes that the tiny pattern is not noise, not an artifact of the electronics or the environment, but a physical greeting from an event that ended long before our species appeared. From one perspective, this is a triumph of control. We have built machines that can measure changes in distance smaller than anything we can meaningfully imagine, then use those machines to open a new window on the cosmos. From another, it is a reminder of how mediated our contact with reality has become. You did not stand under a sky that shook. You looked at a graph, listened to a replayed sound, read a line of text. The universe's voice, when it finally reached you, had already been translated through lasers, mirrors, algorithms, and consensus. Even so, there is something personally disorienting in the thought that, as you sit here, gravitational waves are still passing through you. Supernovae, neutron star mergers, the slow tumbling of dense objects in distant galaxies, all of them send ripples into spacetime. Most are too weak or too infrequent for our detectors to register, but they are there. Continuous, indifferent, altering all distances by tiny fractions without waiting for anyone to listen. LIGO and its successors turn that indifferent background into a selective conversation. The instruments are tuned to a particular band of frequencies, roughly from tens to a few thousand cycles per second, where mergers of compact objects announce themselves with rising chirps. Outside that band, the universe is still speaking. But our ears, our quantum-ruled laser interferometers, are not yet sensitive. As more detections accumulate, patterns begin to emerge, distributions of black hole masses, rates of mergers, hints about how massive stars live and die. Gravitational wave astronomy becomes less about singular events and more about populations. Yet each individual detection is still, at its core, the same kind of thing: a fleeting distortion in the lengths of two long vacuum arms, imprinted on light, then turned into human knowledge. There is an odd parallel between that and the way we experience our own lives. Most days pass without dramatic events. The deep changes, the decisions, losses, and connections that shape who you are show up as small shifts in your routines, in your habits, in the stories you tell yourself. They are ripples in a pattern, noticeable only if you know how to look. LIGO watches spacetime for such ripples, knowing that each one, however brief, carries the memory of something vast and violent that happened far away. None of this makes us central to the universe. Gravitational waves would cross our region of space, whether or not we had ever learned to name them. Black holes would still collide in silent darkness. What changes with instruments like these is our relationship to that silence. We move from imagining the universe as a distant spectacle to recognizing that we are embedded in its vibrations. That even here, on this small planet, the fabric of reality is never quite still. The fabric of spacetime can tremble and pass straight through you, and most of the time, you never know. Entanglement is stranger than that, because it does not just move the fabric. It ties distant pieces of it together in ways that ignore the distances you care about. To step into this part of the story, it helps to let go of the picture of particles as little self-contained beads. Quantum mechanics lets you describe many particles at once with a single wave function. When that wave function can be written as a product of separate pieces, one for each particle, we say the particles are not entangled. Each has its own state. When it cannot be written that way, the particles share a joint state that does not split neatly into individual parts. That is entanglement. The idea rose into sharp focus in the 1930s, when Albert Einstein, Boris Podolsky, and Nathan Rosen wrote a paper asking whether the quantum description of reality could be considered complete. They imagined a pair of particles prepared together and then allowed to fly far apart. If you measure one in a certain way, quantum mechanics lets you predict what a corresponding measurement on the other will show, with certainty, despite the distance. For them, this suggested that the distant particle must have had definite properties all along, independent of the act of measurement. and that the wave function did not tell the whole story. What bothered Einstein was not only the statistics, it was the apparent non-locality of the correlations. How could a choice of what to measure here seem to affect what is revealed there, without any signal crossing the gap at a speed less than or equal to that of light? He called the phenomenon spooky action at a distance, not as a compliment, but as a way of naming his discomfort. For a while, this could be treated as a philosophical dispute. Perhaps quantum mechanics was a clever but incomplete theory, a provisional layer to be replaced by a deeper framework with hidden variables, restoring locality and determinism. Then, in the 1960s, John Bell took a more decisive step. He showed that any local hidden variable theory that tried to reproduce the predictions of quantum mechanics for entangled pairs would have to obey certain inequalities that constrain the strength of correlations between distant measurements. Quantum mechanics predicts violations of those inequalities. Over the following decades, experiments tested those predictions. Photons entangled in their polarization were sent to distant detectors. Spin correlations were measured for pairs of particles separated in space. Each time the tests grew more careful, closing loopholes, randomizing settings, increasing distances. Each time, within experimental uncertainty, the data agreed with quantum mechanics and violated Bell's inequalities. In the second decade of the 21st century, a set of experiments finally closed the most significant loopholes in a single setup, strengthening the case that no local hidden variable picture could reproduce the observed correlations. In recognition of that progress, the Nobel Prize in Physics in the early 2020s was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for pioneering experiments with entangled photons that established the reality of these non-classical correlations. The conclusion is not that information travels faster than light in a way you could use to send a message. Entanglement does not let you shout across the universe through quantum tricks. If you measure your half of an entangled pair, you get a random result, and nothing you do can choose which one. What entanglement changes is the pattern of joint outcomes when you compare notes later. Those patterns are stronger, more tightly linked, than any classical scheme with local hidden properties would allow. So, quantum mechanics tells us that the world contains correlations that cannot be reduced to shared causes in the usual classical way. Two particles that have interacted in the past can remain entangled so that measurements performed on them, even when they are far apart, reveal a kind of connectedness that does not fit the everyday idea of separate objects with separate properties. What each result is depends. In a way, the theory captures, but intuition resists. On the whole, experimental context. Out of this strangeness comes the qubit. Classical computing is built from bits, each of which is either 0 or 1. At any given moment, a classical memory cell has one definite value, a qubit. By contrast, is a physical system with two distinguishable states, often labeled 0 and 1, that can also exist in superpositions of those states. Its full description is a combination of 0 and 1 with complex amplitudes, constrained so that their squared magnitudes add to 1. When you measure a qubit in the computational basis, you obtain either 0 or 1 with probabilities set by those amplitudes. On its own, a single qubit is already richer than a classical bit. But the real difference comes when you have many. Two classical bits can be in one of four possible states at any moment. Two qubits require a wave function spread over 4 basis states at once. 3 qubits need 8. In general, as you add qubits, the size of the mathematical space required to describe their joint state doubles each time. That exponential scaling is what makes quantum computing both powerful in principle and difficult in practice. Entanglement is the glue in that scaling. A collection of qubits that are not entangled can be described as separate states multiplied together, much like independent coins. A collection that is entangled cannot be written that way. Its state contains patterns of correlation that cannot be decomposed into independent parts. Those patterns are what quantum algorithms try to exploit. Structures in a high-dimensional space of possibilities that can be rotated and interfered so that some outcomes are amplified and others are suppressed. Different physical platforms embody qubits in different ways. In superconducting circuits, used by several major companies and research groups, each qubit is a tiny loop or island in which currents or charge can oscillate between two quantized states. In trapped ion systems, individual ions are held in vacuum by electromagnetic fields, and internal electronic levels are manipulated with lasers to encode qubits. In neutral atom machines, arrays of atoms held in optical traps act as qubits whose interactions can be shaped by lasers, allowing entangling gates between selected neighbors. A recent neutral atom quantum computer, for example, has been reported with an array of about 1,225 sites, of which around 1,180 are populated with active qubits. These numbers sound impressive, and at the hardware level they are. But there is an important distinction between physical qubits and logical qubits. Physical qubits are the raw building blocks, each subject to noise, decoherence, and imperfect control. Logical qubits are more abstract entities built from many physical qubits, combined in error-correcting codes that can, in principle, protect quantum information for long times and enable deep computations. At the moment, most quantum devices live in a regime often called noisy intermediate scale. They have tens, hundreds, or in some architectures, more than 1,000 physical qubits, but not yet enough high-quality entanglement and error correction to support many robust logical qubits. Experiments have demonstrated small logical qubit encodings with coherence times extended by factors compared to their components, and even logical entanglement among a handful of such qubits. One recent superconducting processor, for instance, implemented 4 dual-rail encoded qubits with millisecond-scale coherence times and demonstrated multi-qubit logical entanglement protected by an error-biased scheme. You can feel a tension here. The mathematics of entanglement suggests an almost boundless computational landscape. States of many qubits that cannot be efficiently simulated by classical means. Algorithms that promise speed-ups for factoring, search, simulation, and optimization. The engineering reality is more modest. Qubits are fragile. Entanglement is hard to maintain. Noise creeps in from control lines, from materials, from stray radiation, from imperfect isolation. To build a practical quantum computer, you need to do something that, at first glance, sounds paradoxical. You need to use entanglement, which is itself a delicate kind of correlation, to fight the effects of environmental correlations that ruin coherence. Quantum error correction schemes do this by encoding a single logical qubit into many physical qubits in such a way that certain patterns of error can be detected and corrected without measuring, and therefore destroying the encoded information outright. The theory of how to do this is well developed. The practice is still catching up. Even if those engineering challenges are gradually solved, quantum computers will not become universal magic boxes. They are not expected to speed up every task. Many everyday problems remain as hard, or nearly as hard, for quantum machines as for classical ones. The most compelling applications lie in specific areas, simulating quantum systems themselves, factoring large integers for cryptography, searching structured databases, optimizing certain kinds of combinatorial problems, and perhaps solving specialized subroutines within larger workflows. From the outside, this can look like another technology story, new devices, new capabilities, talk of revolutions. Underneath, it is also a continuation of the same quiet confrontation between human intuition and quantum rules. Entanglement was once an embarrassment. a sign that the theory could not be telling a sensible story about reality. Now it is treated as a resource, something to be generated, quantified, and consumed by algorithms. We have not resolved what it means. We have learned how to use it without resolving it. There is a human mirror in that. Relationships in your own life can be understood as a kind of entanglement, not in the technical sense, but as a reminder that your state is not only your own. You are, in part, the pattern of correlations you share with others, the ways their choices constrain you, the ways your actions shape their possibilities. You do not control those ties fully. You cannot send messages into another person's mind by wishing, but the joint outcomes of interactions, conversations, conflicts, shared decisions can be stronger and stranger than you would predict by looking at each person in isolation. Quantum entanglement does not exist to teach that lesson. Yet once you see how deeply inseparability is built into the theory, it becomes harder to maintain the comforting fiction that things, or people, are ever entirely separate. The universe seems to prefer states that cannot be reduced to independent parts. Our descriptions, if they are honest, have to live with that. Still, the core discomfort remains. When we ask whether two entangled particles, flying in opposite directions, each have their own properties before measurement, the theory hesitates. It tells us how to compute joint probabilities for measurement outcomes in various settings. It reproduces those probabilities in experiment with exquisite accuracy. It does not hand us a single, clear picture of what is really happening in between. Interpretations differ on whether there is a deeper story. The data do not. So we do what we often do in the face of such gaps. We move forward with what works. We design protocols for quantum key distribution that rely on entanglement to guarantee that any eavesdropper will leave a detectable trace. We explore quantum networks in which entangled states are distributed between distant nodes, enabling new forms of secure communication and distributed sensing. We test small quantum processors against classical benchmarks, searching for regimes where their entangled dynamics can do something practically useful that no conventional machine can match. In each case, we are stacking devices and algorithms on top of correlations that defied our ancestors' notions of locality and realism. We are building a technological future on a foundation that still feels, in some deep sense, unbelievable. And yet, the equations keep working. The experiments keep confirming. Entanglement, once derided as spooky, has passed every test we have managed to set for it. Instead of resolving our discomfort, it has forced us to live with it, to accept that a theory can be both precise and conceptually unsettling, both unimaginably successful and stubbornly resistant to simple stories. In that way, the quantum world offers a quiet kind of discipline. It does not bend to our desire for a reality that exists fully formed, with properties fixed in advance, waiting to be revealed. It offers instead a pattern of superpositions, measurements, and correlations, tied together by probabilities and by the hard limits of what can be known at once. Qubits and entanglement do not tame that pattern. They only make us more deeply entangled with it. As we build machines whose power depends on a view of reality that still does not sit comfortably with how we like to imagine the world,